to speak? Okay, all right. So it's 11 o'clock, so let's get started on the domain precision session. So we have 3 great talks coming up in this session. So people gather. All right, and also just for anyone who's watching online, we'll monitor Discord to try to grab questions from there. All right, so without further ado, let me introduce the wonderful Roberto Giacobazzi. We'll be talking about how fitting is your abstract domain.
Okay, thank you. So this is a joint work with Isabella, Mastroeni, Elia, Perantoni, and it deals about how the abstract domain represents the information we are considering in program analysis. So we all know that abstract interpretation is sound by construction. Okay, this is the theory. What does it mean? It means that if your specification is precisely captured by the abstract domain, imagine that the abstract domain considers circles. And what you compute are shapes of any kind. Imagine that your specification is a circle, that one in green. But what you compute is a weird shape in blue. Okay, if you abstract what you compute, you get a circle around that blue. This is not abstract interpretation, we all know. This is abstracting the concrete interpretation. Soundness means that when you make abstract interpretation, you may lose precision, but you can still prove that the semantics is contained inside the circle. That's soundness. It may well happen that it's not always complete, actually almost never complete. And when it is incomplete, it happens that during the abstract interpretation, you lose so much precision that you get out to the respect to the specification, and you produce something called false alarm. So you cannot prove what you want to prove. There are notions of completeness that are global, namely you ask to be complete for all possible inputs. This is a very restrictive case. Or it can be local. This is a relatively newer notion that we've studied about a couple of years ago, and resembles pretty much looks like what in model checking is the CIGAR, the counterexample abstraction refinement, where you go through along the trace and you try to refine the domain with respect to that computational trace. So not with respect to all possible inputs. This is completeness. But remember that we need to use to consider this aspect. That means that the abstract domain has to be able to represent the specification. So when you consider precision, you have to consider how the abstract semantics and the abstraction of the concrete semantic relate with each other, but also how the abstract domain is able to express the information. Completeness controls the relation between the first two, namely between the abstraction of the semantics and the abstract interpretation. This is completeness. When you have equality, you are complete. When you have inequality, you have just soundness. But if the abstract domain is just I don't know, you are complete. So that produces no information at all. So you need to have an abstract domain rich enough to express the properties you want to talk about. So the loss of precision is not only, therefore, within this red arrow, but also with respect to what the abstract interpreter compute with respect to, for instance, the property of I don't know. So is the abstract interpreter able to produce something better than I don't know? That's the question. How can we model this inside the computation? We introduced the notion of adequacy, which is somehow the qualitative counterpart of a notion of partial completeness that we introduced with Mila and Marco in Popul 2022, where instead of having qualitative relation between the precision of the points in the abstract domain, so a distance, here we simply consider whether something is below the top element, which is I don't know. So if is able to produce some answer. So adequacy controls the representability and not the completeness. And indeed, we will see that the two notions are completely incomparable. Of course, you can relate with the top element, that means I don't know, and say, I want to try to prove whether my abstract interpreter will produce a better result than I don't know. okay? Which is, of course, sound, but means nothing. You can play this game for top, which is I don't know, but also for any threshold you put. So you can say, well, I want to prove that my abstract interpreter is able to produce a result which is better than some given property, no matter what in the abstract domain. So the adequacy is defined in this way. Again, we have a notion of global adequacy and local adequacy. Global adequacy means that for all possible input, property in input, this is the best correct approximation. So this is the best correct possible abstract interpreter, okay? That is below the threshold, strictly. So it produces something better with respect to the precision of the lattice of abstract objects in my abstract domain. Locally, the same notion plays when you have that this has to hold for a specific input, not for all possible inputs. Look at this. Okay, in the paper you will find other domains. You will see here the very stupid sign abstract domain, which is the usual one that we use for showing things and make them a little bit stupid. But in the paper you will find intervals, octagons. So there are nicer abstract domains for which all this game plays in the same way. So imagine that you consider this abstract domain, which is sign. Okay, the adequacy. You will see that if you put as threshold, I don't know, so if I want to see whether with respect to that specific input, my abstract domain sign and the transfer function that multiplies by 2 is adequate, okay, whether the abstract domain sign is adequate for that specific input and that transfer function and that precision threshold, then I can easily see by computing this line that this holds. So indeed, it is adequate. Indeed, we produce something which is a point of all the positive numbers, which is strictly below all non-negative ones. This is adequate. It may well happen that this doesn't hold for all possible inputs. So it depends on the input. It depends on the transfer function. It depends on the abstract domain. You take this simple input, same transfer function, and you get that the result is definitively top. So is I don't know. This is not adequate. But look, it's complete. So in this case, the relation between the abstraction of the semantics and the abstract semantics is an equality. So that means that completeness doesn't imply adequacy. Look at this. Now you change, you keep the same input, -1, 0, and 1, but we change the transfer function. Transfer function now is n plus 2 to the square. This is non-complete, and you will see there, but it's adequate. So once again, the two relations are totally unrelated, okay? The two notions are totally unrelated. Okay, so we try to play the game, the usual game in abstract interpretation, which is, okay, we have a property, we want to achieve a goal, then we can make in two different ways. Either by refining the abstract domain towards that goal, or changing the program towards that goal. The second one, we didn't touch it at all, so it's probably future work, and it's some discussion in the conclusions. We did it in the domain refinement. So, how to make it? It's funny and interesting that the way we make the abstract domain adequate looks pretty much the same as the way we make completeness. So we actually use the same technicalities inside the refinement. Of course, the necessary condition for being adequate for an abstract domain, a transfer function f and an input c, is that this picture holds. Namely, there is the function f applied to c is below the threshold. So what's happened? Suppose that now the refinement, as usual, and the same game plays exactly the same in completeness. We have an input refinement and an output refinement. So we can refine either by input, refining the abstraction in input, and the abstraction in output. And the two refinements need to cope. So if we want, in the end, to have one single abstract domain, for both input and output, we need to iterate the refinement towards a fixed point. So what we need to add? Take the set of all points, D, okay, that are above C and have the same abstraction as C, and produce, by applying the transfer function, something that is below the threshold. Pick up one maximal element from that set, okay? That is the point, one of the points that we may add to the abstract domain. There's a problem here. There is not a unique refinement, so-called, there is not a best refinement. There are many possible refinements that produce adequacy for that domain. And this is a refinement in input. Indeed, we are producing the maximal element in input that will be mapped to something below the threshold. We can do the same in output, exactly the same structure. So what we do here is we pick up the maximal output of the threshold function, of the transfer function, applied to the points that have the same abstraction in the input. And that element, which once again may not be unique, is added to the domain to become refined in adequacy. So, an example, back to the non-adequate sign domain for this little input and this transfer function. The threshold now is not anymore the top, I don't know, but is a non-negative number, any non-negative number. So what are the maximal elements to consider in input? Well, the maximal elements are there are infinitely many, any non-negative number minus one number. Okay? So I need to pick up one of them. Which one? You will see that the one that best fits to the example depends on the input. Okay? So, of course, these are the maximal elements in the set, so they satisfy the condition that the transfer function is below the threshold, and the abstraction is exactly being non-negative. We add to the abstract domain the set of non-negative minus 8. You say, why a minus 8? Well, look, look at the set in input. So it's the input that produces the way we pick up the easiest element. That abstract domain has a new point, so it's not anymore sign, but it's sign plus the fact that you may have an integer which is non-negative and not 8. And then look what you compute. You abstract this set into the new domain, and you get something which is this one. This set, which is strictly below, this is not an abstract point, this is strictly below the threshold, because the threshold is being non-negative. But again, this doesn't satisfy completely the adequacy, because what's happening here is that you're becoming adequate from the input, but not for the output. So you need to iterate the refinement once again. And look what you will get now is that you add to the domain a new point, which is z minus 16, which is exactly twice 8. So we are computing in the output now the transfer function. And now what you get is exactly an adequate abstract domain. Look, the new point here that is produced here is because the abstract domain is a Moore family. So whenever you have 2 points, you have the conjunction of the 2 points, and you produce new elements in the abstract domain. And this will become adequate. So the refinement is an iteration of refining input, output, and until you reach a fixed point. Of course, the way you pick up the elements depends strictly on the input for which you want to be adequate. I conclude with a simple program logic. So now, I mean, if you want a paper to be accepted, you have to have a program logic inside. So we made it, and we pick up a very simple syntax. The simple syntax is regular expressions. So this expresses very well the structure of control flow graphs. The abstract semantics is made in the most simple way. This is the most straightforward abstract semantics. It simply takes the best correct approximation of the basic expressions and then compose them. Of course, the abstract semantics is not the best correct approximation because compositionality is not preserving best correct approximation property. So this is the best semantics, the best simple semantics you can build inductively on that syntax. And then we define triples. The triple is this. It says, well, we can prove in the proof system this triple, meaning that the abstract semantics of the input assertions C produce something that is below the abstraction of the post condition D. And that is below the threshold. So all this is below. Basically, if we are able to prove that triple, it means that the abstract interpreter will be surely below the threshold, therefore will surely produce a better result than the threshold I'm saying. Okay, and that's the rules, that's the logic. In the paper you will find all the theorems and the proofs that justify that this proof system is sound, but not complete, of course. I just want to point out that there is an interesting rule that is exactly the copycat of a rule that we used in the program logic for local completeness, which is the so-called relax rule. The relax rule says that you can always relax the input assertion, so it goes the other way around with respect to the traditional logic. You can always relax the input assertion up to, you have to be sure that you are in the bound of the abstraction. So you are in something that will be mapped to the same abstract element, which is this one, gamma alpha C prime. And you can shrink the post condition. But you need to be inside the same set of elements that are mapped by the abstract domain into the same point. It's interesting because the two notions are completely unrelated, completeness and adequacy, but the proof system looks pretty much the same. Why? I have no idea. Okay, that's very simple. Then, for instance, we want to prove this triple. Okay, and well, basic assertions, we can prove that these two holds, namely, these are the basic assertions, so the basic expressions in my language, and therefore we can prove this. Then by composition, we go on, and in the end, we are able to prove that the post condition is exactly Z equals 0. And that is below the threshold. Conclusions. So adequacy can be used. I mean, the fact that it's useful is another story, but can be used, can be used to prove whether my abstract interpreter truly incorporates something, an information that is better than the threshold I'm considering. So it somehow is a kind of quality measure of my abstract interpreter with respect to a threshold that I want to consider. So if I build an abstract interpreter, I want to have some limit of precision. I fix that limit. I have a proof system that tells me whether my abstract interpreter will satisfy that limit. More interesting is that adequacy as completeness is a totally intentional notion. It depends on the way programs are written. Why this? Because the abstract interpreter, the result of the abstract interpreter depends on the way the program is written. You can write the code in two different ways, producing the same result, but having completely different abstract interpretations. So it's an intentional notion. So the question is, can we now in the paper we transformed the abstract domains to achieve adequacy, but the question, can we transform programs to achieve adequacy? That means that I better fit my code to my abstract interpreter instead of fitting the abstract interpreter to the code, which is abstraction refinement. The second one is that, actually, the second one is the one I just said. The first one is this one. Whether I transform the code in such a way that my abstract interpreter becomes inadequate. And that is exactly code obfuscation in the end. Is once again a way on which I transform my code, and in the end my abstract interpreter produces, I don't know, as a result. Namely, is unable to extract any useful information. Thanks.
10 minutes for questions. Plenty of time.
That was a very interesting talk. I don't know if you will roll your eyes at this, Roberto, because it's about use, but the notion of adequacy seems to be related to the concept of widening up to. So when you do widening up to, you have like an invariant that you're trying to discharge, but your default widening is not strong enough to discharge that invariant. So you do this on-the-fly refinement of your widening, which is a bit like your threshold refinement. But in that CAV paper, there was no notion of this iterative technique.
Totally agree with you. Yeah.
Oh, okay. Fine. Thank you.
I mean, you can't, I think that the same technique, I mean, somehow this is made on the abstract domain in standard Galois connection, but I think you can play this similar game in the widening.
Yeah.
And you adjust the widening to thresholds, and you see whether you can do that, up to what limit you can do that.
Yeah. Okay, cool. Thank you.
Other questions?
Very good talk. So my understanding is that you refine the abstract domain, like for instance when you went from sign to sign prime to sign double prime. My question is more about what are the what's the advantage of refining the abstract domain versus just trying to develop like more precise abstract transformers, but in a simpler abstract domain in order to like kind of attain the precision that you're going for?
That's exactly the question I raised in the end. Mm-hmm. Changing the predicate transformer somehow is driven by the code.
Okay.
So that's what is lacking in the paper is exactly your question.
Okay.
I think it would be very interesting to develop a completely symmetric approach where instead of changing the abstract domain, so you keep the abstract domain very simple, as simple as possible, and you try to morph the code and therefore the transfer function in order to fit that.
Right.
That's actually we did that and we are doing that. Actually, is now starting a project in my university exactly in this specific case for completeness.
Oh, okay.
For adequacy, I don't know. It's something to be done.
But great talk. Thank you.
Thank you.
Other questions? Got a little bit more time.
Okay.
Okay, I'll ask one then. I think I may have just missed this or something, but like, what guarantees that your refinement process terminates?
Oh, in the end, you may boil down into the concrete domain. So,
so not necessarily. Or?
Not necessarily. Well, in principle, yes, it may happen. You can stop whenever you want. I mean, right. you fix an amount, a percentage of adequacy of your abstract domain with respect to your input, and then you stop there. It's important the way you pick up the elements in order to reach the limit, because in the case of completeness, you have a complete share, so you have the best possible refinement in the global case. In the local case, no, there are many possibilities, and in the adequacy, it's exactly as in the local case, you have many possibilities to reach. So that's a fixed point strategy that has to be completely studied from scratch, because we didn't know at the moment.
So how difficult would be to automate this procedure? I mean, checking adequacy or inadequacy?
I think it's difficult. I mean, the impression, Elia Perantoni tried to make, he made an implementation of that, pretty toy implementation, where it was running on simple abstract domains, signed intervals, we'd stop it there. It was okay, but I think the way you pick up, I mean, it has to be assisted by the user, because you have to provide some knowledge. Then I don't know if a large language model eventually will produce some good result in picking up the right points from the concrete domain, maybe. Okay.
Others? Okay. Double check the online again. All right. Okay.
Okay.
Well, with that,
Thank you.
thank you, Roberto.